Okay, let's dive into this. Welcome back, everyone. Today, we're pulling back the curtain on the secrets behind massive web architecture. Because if you've ever built a website or an app, getting it to work for a handful of people, that's one thing. But getting it to work flawlessly for a massive, global audience, that is a completely different beast. So, we're going to break down the invisible infrastructure that keeps the modern web alive. And I promise you, it's a whole lot more fascinating than just writing code.
I mean, think about it. How do mega sites like YouTube, Netflix, Google, or Facebook handle hundreds of thousands or literally millions of simultaneous users every single day without just exploding? The sheer volume of data and requests happening every single second is mind-boggling. And behind these massive platforms, there isn't just one giant supercomputer doing all the heavy lifting. It's actually this beautifully orchestrated army of servers working together. Today, we're going to explore exactly how they manage all that traffic.
But to really understand the solution, we first need to understand the problem. So picture this. You've got a standard Linux web server. You're running Nginx, maybe some Python Flask or Node.js on it. When you first launch, everything is perfectly fine. A few users drop by, and the server handles it with no sweat. But what happens if you get featured on the front page of a major news site, or a video about your app goes crazy viral? Suddenly, you have this massive spike, and boom, 100,000 concurrent users try to hit your site at the exact same millisecond.
Now here's exactly what happens to that poor, solitary server, and, spoiler alert, it is visceral and immediate. First off, your CPU spikes straight to 100%. It literally just cannot process the math fast enough. Then your memory is completely exhausted, and you get hit with that dreaded out-of-memory error. Meanwhile, your TCP connections absolutely explode because the server is frantically trying to juggle way too many open lines of communication at once. The whole website slows to a painful crawl, and finally, total catastrophic failure. Server down.
Naturally, the most intuitive fix for an engineer is to say, okay, well, if one server isn't enough, I'll just add more servers. So you boot up Web 1, Web 2, and Web 3. But wait, that introduces a completely new complication, the routing dilemma. When a user tries to access your site, how do they actually know which specific server to connect to? It's not like you can just ask the user, hey, could you please connect to Web 2 today, right? That leaves us with a massive bottleneck of confusion.
So the crucial point is, you need a traffic dispatcher. Enter the load balancer. Think of this as the ultimate traffic cop for the internet. Its entire job is to sit right in front of your servers, take that massive, chaotic wave of incoming traffic and evenly distribute it across your multiple back-end servers. By splitting up all that work, the pressure on any individual machine drops dramatically. And just like that, your website can suddenly support exponentially more people.
Now you might be wondering, how does the load balancer actually decide who goes where? Well, it's not just guessing. It uses specific algorithms. The absolute most common and straightforward approach is called the round-robin algorithm. It basically just strictly takes turns. So the first user gets sent to Web 1, the second user goes to Web 2, the third goes to Web 3, then the fourth user cycles right back to Web 1, and it just repeats the whole process. It's incredibly simple, yet highly effective for keeping the workload perfectly balanced.
However, sometimes simple turn-taking just isn't enough, right? Load balancers can actually be incredibly smart. Let's say you're running a heavy streaming site or using WebSockets. In that case, you might use the least connections algorithm. This one dynamically assigns the newest user to whichever server currently has the lightest workload. Pretty clever. Or, if you have a site where a user needs to stay logged in and keep their session data intact, you'd use IP hash. This actually pins a specific user's IP address to the exact same backend server every single time they visit.
Now, if you've poked around web architecture, you'll often hear the term load balancer thrown around in the exact same breath as reverse proxy. People mix them up all the time, but understanding the difference is a massive aha moment. See, a forward proxy, kind of like a corporate VPN, helps you, the user, go out to the internet safely. But a reverse proxy acts in the exact opposite direction. It sits in front of your web servers to handle the internet coming to you. The reverse proxy is basically the ultimate front door of your website.
And let me tell you, this front door does an unbelievable amount of heavy lifting behind the scenes. It literally has superpowers. First off, it completely hides your actual backend servers. The outside world only ever sees the reverse proxy, which completely protects your vulnerable Python or Java code. It also manages caching, meaning it serves up popular images instantly so your backend doesn't even have to work for it. It automatically compresses traffic using gzip or Brotli to save on bandwidth. Oh, and it often acts as a web application firewall, blocking DDoS attacks and SQL injections before they even touch your application. Seriously, it does the whole shebang.
But perhaps its greatest trick of all is SSL and TLS offloading.
Look, handling the encryption and decryption for secure HTTPS traffic takes a massive amount of computing power. If your backend servers had to do that for millions of users, they would just choke. Instead, a reverse proxy like Nginx intercepts that encrypted HTTPS traffic, decrypts it right at the front door, and then passes fast, unencrypted plain HTTP backward to your servers. It saves an absolute ton of processing power for your actual application.
And this brilliantly illustrates why specific tools have totally taken over the web. Let's compare traditional Apache to Nginx. In the old days, Apache created a brand new process or thread for every single user connection, with massive traffic that eats up your server's resources instantly. But Nginx created a total revolution. It uses an event-driven, non-blocking architecture. That basically means just a tiny handful of worker processes can manage hundreds of thousands of connections simultaneously without even breaking a sweat. It is just incredibly lightweight.
And that precise non-blocking superpower is exactly why tools like Nginx are the absolute foundation for modern cloud infrastructure today. Seriously, if you look at CDNs, API gateways, or modern setups like Kubernetes ingress controllers, they are all leaning on this exact technology. In Kubernetes, for example, an ingress controller is fundamentally just a reverse proxy and a load balancer mashed together. Whether it's Nginx, Traffic, or HA proxy, they are the vital traffic managers in any modern containerized environment.
Now, what's really interesting about this slide is how remarkably simple it actually is to configure this powerhouse. Honestly, you might expect lines and lines of complex code, right? But to set up a basic reverse proxy in Nginx, you literally just tell it to listen on port 80 and then use the proxy_pass directive to point it to your backend server running locally, like say a Flask app on port 5000. That's it. The user hits Nginx and Nginx seamlessly routes them to the Flask app. It's absolute elegance through simplicity.
Let's move to more end and see how this builds into the real world. What we're looking at here is the vertical architecture waterfall of a modern tech stack. So traffic flows from the internet, hits a global load balancer, passes through a web application firewall, goes into a reverse proxy like Nginx, which then routes it down into Docker containers orchestrated by Kubernetes, and finally, hit your actual microservices. This layered defense and distribution is exactly how the big players survive.
It's super important to remember this fundamental reality. When millions of users flood a website simultaneously, the hardest part of keeping the site online isn't the programming code. I mean, it isn't your flashy JavaScript or your clever backend logic. The true, grueling work is managing thousands of TCP connections, allocating caching, maintaining session states, and distributing the load. The load balancers and reverse proxies, they are the true traffic cops keeping the internet from devolving into total chaos.
Which brings us to this incredibly powerful summary. If there's absolutely one thing you take away from this explainer today, it's this quote right here. The true core of the modern web isn't HTML, CSS, or JS. It's Linux plus NGX plus load balancing. That combination right there is the unsung hero. It's the absolute bedrock that allows our modern, high-speed, always connected digital world to actually function.
I really hope this cleared up the mystery of how massive websites actually survive the internet for you. But I do have a thought to leave you with. As artificial intelligence and spatial computing start demanding even more massive instant data transfers, will Nginx and load balancing be enough to save us? Or are we on the verge of needing a completely new architecture for the web? Let me know what you think in the comments. If you found this explainer helpful, please hit that like button, subscribe, and turn on notifications. Thanks so much for focusing in with me today, and I'll catch you in the next one.